Welcome to the deep dive. Today, we're getting into something pretty mind-bending, quantum computing.
Yeah, definitely a big topic. We've got a stack of material here, principles, applications, the challenges, you name it.
Right. And our mission, as always, is to cut through that complexity. We want to give you the essential insights, kind of a shortcut to understanding what this quantum revolution is really about.
Exactly. Focusing on the fundamentals, the real potential, and importantly, the hurdles, not just the hype.
Okay, so let's start at the beginning. The absolute core difference between quantum and classical computing. It comes down to the bit, or rather the qubit, right?
Precisely. Your classical computer uses bits that are either 0 or 1, simple on-off switch.
Huh?
A qubit, though, it's different. It can be a 0, it can be a 1, or crucially, it can be in a superposition of both states at the same time.
Okay, superposition, that's the quantum weirdness starting, existing in multiple states at once.
That's the one. Think of it maybe like a spinning coin. It's neither heads nor tails until it lands, until you measure it. The math involves probability amplitudes, basically telling you the chance of finding 0, 1 upon measurement.
And the formula, alpha 0 wrangle plus alpha 1 1 wrangle. That just shows those probabilities.
Yeah, alpha 0 squared is the probability of getting 0, alpha 1 squared is the probability of getting 1. But the key thing is, before measurement, it is in that combined state. And when you have multiple qubits, say n of them, they can represent 2 to the power of n classical states simultaneously. That's exponential scaling. Huge difference.
Wow, okay. And then there's entanglement, the spooky action.
Right, entanglement. Another core concept. You link 2 or more qubits,
Yeah.
and they become correlated in this spooky way. If you measure the state of one, you instantly know something about the state of the other, no matter how far apart they are.
Instantly.
Instantly. It doesn't transmit information faster than light, but the correlation is immediate. It's a vital resource for computation, adding to that exponential power.
So superposition and entanglement work together. What about interference and measurement?
Good point. Quantum states act like waves, so they can interfere. Think waves in a pond, they can add up or cancel out. Quantum algorithms use interference to sort of amplify the probability of getting the correct answer and cancel out the wrong ones.
And then measurement collapses it all down.
Exactly. Measurement forces the qubit out of superposition into a definite state 0 or 1. And it's probabilistic, based on those amplitudes we mentioned. You often run the algorithm many times to get the likely answer.
Okay, so the processing is fundamentally different. Not just faster silicon, it's a whole new logic.
Totally different. Classical uses sequential Boolean logic, gates A and D, or not the n-type. Quantum uses quantum gates that manipulate these superposition and entangled states.
And the hardware reflects that. You mentioned superconducting circuits.
Yeah, that's one popular approach.
Yeah.
They need to be kept incredibly cold, near absolute zero, to work. Others use trapped ions, photons, neutral atoms, each with pros and cons. But they all need extreme environmental control. These quantum processing units, or QPUs, usually act as coprocessors alongside classical systems.
Not replacing my desktop then, more like a specialized engine for specific jobs.
That's the idea for the foreseeable future, yes. They offer this potential exponential speedup, but only for certain types of problems.
Which brings us to cryptography. This is the big one everyone talks about, the quantum threat.
It is a major concern, absolutely. A lot of our current encryption, like RSA, relies on problems that are incredibly hard for classical computers specifically, factoring large numbers.
Right, like finding the 2 prime numbers that multiply to give your huge public key.
Exactly. Or the elliptic curve discrete logarithm problem for ECC, believed intractable classically for large enough keys.
But not for quantum computers, because of Shor's algorithm.
Correct. Peter Shor developed a quantum algorithm back in the 90s that can, in principle, solve both integer factorization and discrete logarithms exponentially faster. It uses something called the quantum Fourier transform.
Exponentially faster, that sounds bad for security. How many qubits are we talking?
Well, it depends, and it's complex. We need logical qubits, which are error-corrected qubits. To break something like RSA 2048, estimates range, but you're likely looking at thousands, maybe even tens of thousands of high-quality logical qubits.
Logical qubits, meaning you need way more physical qubits to make one stable logical one because of errors.
Precisely. Qubits are incredibly fragile. They lose their quantum state, decohere very easily due to noise, temperature fluctuations, anything really.
Yeah.
Quantum error correction, QEC, uses redundancy to protect the information, encoding one logical qubit across many physical ones.
Got it. And this Shor's algorithm threat leads to the harvest now, decrypt later scenario.
Yes, that's the worry. Adversaries could be recording encrypted data now, even if they can't break it yet, and just wait until they have a powerful enough quantum computer. Q-Day, some call it. It creates real urgency.
So what's the defense? Post-quantum cryptography or PQC?
That's the main line of defense, yes. Developing new cryptographic algorithms that are resistant to attacks from both classical and future quantum computers. It's different from quantum key distribution, QKD by the way, which uses quantum mechanics for key exchange, but not encryption itself.
Okay, PQC. What kinds of algorithms are we looking at?
There are a few main families. Lattice-based cryptography seems very promising, things like crystals Kyber and dilithium. Good security, pretty efficient.
NIST, the U.S. standards body, pick those, right?
Yes, NIST has been running a multi-year competition to standardize PQC algorithms. They finalized standards for Kyber, for key encapsulation like secure setup, and dilithium for digital signatures in August 2024. Also Falcon, another lattice signature, is expected.
Any other types?
Hash-based signatures like Sphinxius plus AJ are another category. Very secure, based on well-understood hash functions, but can be a bit slower or have larger signatures. There were also code-based, multivariate, and isogeny-based approaches, though some faced setbacks.
And NIST's process was important. Public scrutiny.
Absolutely crucial. Years of analysis by cryptographers worldwide to try and break these things. Builds confidence.
But migrating everything, that sounds like a massive job.
It's a huge challenge, finding all the places encryption is used, dealing with performance impacts, legacy systems that can't easily be updated, costs, just organizational inertia. It's a big lift.
So systems need to be designed to swap algorithms easily. Crypto agility.
That's the buzzword, yes. Designing systems to be crypto agile is key. Some are looking at hybrid approaches too, using both a classical and a PQC algorithm together as a transition. Governments are setting deadlines, like the U.S. aiming for migration by 2035.
Okay, shifting gears a bit. Beyond breaking codes, what about the potential in, say, medicine or biology?
Ah, yes, this is where it gets really exciting on the constructive side. The ability to simulate molecules accurately at the quantum level could be revolutionary for drug discovery.
How so? Like predicting how a drug will actually work?
Exactly. Simulating how a potential drug molecule binds to a target protein, or modeling chemical reactions with quantum precision. Classical computers struggle with the complexity of these quantum interactions for all but the smallest molecules.
So things like designing new drugs or screening candidates virtually.
Potentially, yes.
Right.
Algorithms like the variational quantum eigensolver, VQE, are being explored for this. Also accelerating genomic analysis, finding patterns in huge DNA datasets for personalized medicine, maybe even using quantum machine learning, QML, on complex biological data.
QML, that's applying quantum principles to AI.
Sort of, yeah. Applying quantum algorithms to machine learning tasks could potentially help analyze complex medical images like MRIs or CT scans faster or find subtle features, though QML is still very early days compared to classical ML.
And protein folding, that's famously hard.
Incredibly hard, classically. While things like AlphaFold have made amazing progress using classical AI, simulating the dynamics and subtle quantum forces involved in folding and interaction is still a huge challenge. Quantum computers might offer a way to tackle that directly, modeling enzyme catalysis, photosynthesis, lots of complex biological processes.
Sounds amazing, but it all comes back to actually building these machines. You mentioned different qubit types.
Right. There's no single winner yet. Superconducting circuits, like Google and IBM use, are fast but need extreme cold and have relatively short coherence times. Trapped ions, used by IonQ and Quantinuum, are very stable and high fidelity, but can be slower to operate.
Others too, photonics, neutral atoms.
Yep, photons offer potential for networking and room temp operation, pursued by Sequantum and Xanadu. Neutral atoms, from companies like Quera and Pascual, allow for large numbers of qubits. Then there are topological qubits, which Microsoft is betting on, theoretically very robust but hard to create, and spin qubits in silicon. Each has trade-offs.
And the big enemy for all of them is decoherence, losing that quantumness.
That's the constant battle, yes. Protecting the delicate quantum states from the noisy outside world. Coherence time, how long a qubit stays quantum, is a critical metric.
Which brings us back to quantum error correction, QEC.
Absolutely essential for large-scale, useful quantum computers. The goal is fault-tolerant quantum computing, FTQC, where logical qubits are robust enough for complex calculations.
But QEC is hard, needs lots of extra qubits.
Very hard. The overhead in physical qubits needed for one logical qubit can be huge, maybe thousands to one initially. Plus, you can't just copy quantum states to check them. The no-cloning theorem prevents that. But there's been real progress recently.
Oh yeah, Like what?
We're seeing experiments demonstrating the basic principles of QEC codes, like the surface code, showing logical qubits with lower error rates than the physical qubits they're made from. Performing basic operations on logical qubits, it feels like we're entering an early QEC era. Still a long way to FTQC, but definite progress.
And then just scaling it all up, manufacturing millions of these things consistently.
Exactly. Huge engineering hurdles remain. Manufacturing reliable, identical qubits in large numbers, interconnecting them, controlling and reading them out efficiently. It's incredibly expensive, needs specialized infrastructure, and frankly, there's a shortage of people with the right skills. These challenges are all interconnected.
So who's actually doing all this work? It sounds like a massive ecosystem.
It really is. You have the big tech players, IBM, Google, Microsoft, Intel, Amazon pouring in resources. Then many specialized quantum companies, the ones we mentioned like IonQ, Quantinuum, Rigetti, D-Wave, Pascal, Atom Computing, and many others, each often focusing on a specific qubit technology or part of the stack.
Software too.
Definitely. Companies focus just on quantum algorithms and software like Classic or Riverlane, plus leading universities and government labs doing fundamental research. And cloud platforms from the big players are making quantum processors accessible for experimentation.
Any recent milestones making waves? Claims of quantum advantage?
There's always activity. We're seeing continued progress in QEC demonstrations from multiple groups. Roadmaps from IBM, Atom, IonQ, etc. target hundreds or thousands of physical qubits in the next few years. There are ongoing claims of quantum advantage for specific, sometimes contrived, problems or simulations like from D-Wave or IonQ.
But classical algorithms keep improving too.
Exactly. It's a moving target. True practical quantum advantage for a real-world problem is still debated and likely requires fault tolerance. Benchmarking progress is also getting more sophisticated.
And governments are heavily involved. Global race.
Oh, absolutely. The U.S. National Quantum Initiative, China's massive investments, the EU Quantum Flagship, programs in the UK, Germany, Canada, Japan, significant government funding globally, often alongside venture capital. It's both competitive and collaborative.
So summing up, we're kind of in this near-term intermediate scale quantum NICU era now, right?
Yeah.
Exploring what today's noisy machines can do.
That's a good way to put it. Using heuristic algorithms like VQE, developing error mitigation techniques, since full error correction isn't there yet, trying to find niche applications where even these imperfect machines might offer some value.
While the long-term vision is still that fault-tolerant machine.
That's the ultimate goal, yes. FTQC is needed for the really disruptive applications like Shor's algorithm or complex simulations. Timelines vary wildly depending on who you ask, but significant breakthroughs in qubit quality, scaling, and especially QEC are still needed. It's a balancing act showing near-term progress while investing for that long-term vision.
Okay, that's a lot to digest. So, quick recap. We've covered the basics, qubits, superposition, entanglement, the big difference from classical computing. We looked at the serious threat to cryptography and the vital shift to PQC.
Right, and then the potential upside in medicine, material science, simulating nature at its own level.
We touched on the immense challenges of actually building these machines, the different qubit types, the fight of decoherence, the critical need for error correction, and just scaling up.
And the vibrant global ecosystem pushing it all forward. Big tech, startups, academia, governments. From the near-term NISQ era explorations to the long-term FTQC dream.
Hopefully this deep dive has given you, our listener, a solid practical understanding of where things stand with quantum computing right now.
Yeah, cutting through some of the confusion and, keeping an eye on that error correction progress is probably key.
Definitely. Which leads to a final thought for you to ponder. What if those QEC breakthroughs arrive faster than many predict? If the path to fault-tolerant machines suddenly shortens, how might that compress the timeline for impact? Think about cybersecurity, drug discovery, AI. Could the next decade look radically different? Something to chew on. Thanks for joining us for this deep dive.